next one is by Jonas Höfer, a progress report on constructive higher presheaf models of homotopy theory.
Yeah, thanks for the introduction. And yeah, as maybe the somewhat defensive title says, this is work in progress, but we actually made quite a lot of progress since we wrote this title for the abstract. There's still some unfinished parts, but I will talk about this sort of when we come to it. And also, this is of course joint work with Thierry and Christian. So, okay. So first, as the title says, we work in a fully constructive setting. So by now we have quite a lot of machinery to build sort of many different models of HoTT. For example, classically, there's the Schulman result, but constructively, the picture is somewhat different. We have different models of spaces with cubical sets, but there are less tools to build the analogs of presheaf models, which we maybe want to justify certain extensions of HoTT. And yeah, there's certain reasons why I could be interested in that. I mean, first, it's of course interesting to somehow justify this theory in a weaker meta theory to see what we really rely on. And the other thing is, if you can do these model constructions constructively, you can internalize them into other models of extension type theory. So, for example, for the model of synthetic algebraic geometry, there are some external parameters which you could choose as something you have in some model. Okay, so as I said, the general goal is somehow to build presheaf models of HoTT, and there is some existing work on that. And sort of the key novel thing we want to do is we want to do it on internal categories in cubical sets. Why we want to do that is something I will talk about in a moment. And sort of the key applications of something like this is the justification of these synthetic approaches, where you take HoTT, you extend it with some axioms, and then you prove something about interesting mathematical objects in this synthetic setting. So to justify these kinds of settings, you need some notion of sheaf model of HoTT. The sheafification part can usually be done in some kind of Lex modality. So this part is about the first part. How do we get the presheaf model where you can define these Lex modalities? Okay, right. Before I can tell you what you somehow gain from this work, I first have to take something away, and I have to talk about a somewhat subtle bug in an old paper, namely in the SAG paper, so the one for synthetic algebraic geometry. There is a model of the axioms, but in a constructive meta theory, this model does not quite work. There are instances where it breaks, and this is sort of the motivation for this work. So what's the setup? Somehow you look at cubical presheafs over some category of K algebras for some ring. And in there, you can define this generic ring, which is just the presheaf or the cubical presheaf that maps a K algebra to its underlying set, but as a discrete cubical set. So no non-trivial paths. And then one of the key axioms you want to prove is this duality axiom, which essentially says if you take the generic ring, you adjoin some variables, you quotient out some polynomials, then you can look at the canonical function that sends such an object to something in this type on the right, which is the generic ring exponentiated by essentially the type of solutions for such an equation system we have on the left. So these polynomials specify a system of equations in n variables. And the axiom says that this particular map is an equivalence. But this is a bit problematic if we want to do this in this setting where we have cubical sets, so where we have spaces instead of actual sets, because the object on the left, that's some higher inductive type. But the object on the right is somehow a very strict thing because it just involves the generic ring, which is just defined in terms of strict sets. And these paths, they will also be actual equalities because of that. So the issue now is that the axiom, it holds if we instead talk about a strict quotient because it holds in the one-toppers. So now what happens is by 2 out of 3, the axiom in the sense of the hit will hold precisely if we can strictify homotopy quotients into strict quotients. But this is something you cannot expect in general in a constructive setting. And this sort of is the issue we try to work around. We will try to work around. Okay, so let's maybe leave it at that with the issue. So what's the fix? The fix is we don't work with this one category of K algebras. Instead, we want to work with a category internally to cubical sets. So one way of describing this is a cubical presheaf valued in categories. And we want it to be essentially the type of K algebras that are zero truncated. So morally, they are still sets, but they can have somehow non-trivial higher structure. It's just that this structure is from the point of view of HoTT irrelevant. Okay. One issue there you have to solve is somehow you want a strict internal category. So you want strict composition still, even though you have a cubical set of objects and morphisms. And there's a way to fix this, which is, I guess, very similar to some of the tricks we saw before. So we can define this category in HoTT. The problem there is we have to state certain preservations of equations. So for example, we have to say a homomorphism applied to an addition of two things is the sum of the two things. But this is not strict because if you compose those, you have to compose paths. Instead, you phrase this as a relation. So you say if x plus y is equivalent to z, then h of x plus h of y is equivalent to z. And that's sort of a neat ad hoc construction to make this category strict. So from the point of HoTT, this turns it into a category where everything is proven by reference. Right, and this trick, it works in general for some category C by looking at the image of Univalent, and then you somehow have to encode this naturality condition in a similar relational style. So I first learned this trick from Christian. I'm not quite sure where it originates. Yeah. Okay. So with that, we obtain a strict internal category in cubical sets, and that we can now use to actually build models of HoTT. So it's a well-known sort of topospheric fact that if you have an internal category and you take internal presheafs on it, then it's actually presheafs on some other category, namely this Groton deconstruction of C. So the objects are just pairs of your base category, so cube in this case, and then objects of the corresponding category. So this category we can now relate to our original notion of cubical sets. So I'm not being precise about which cubical sets we're using. It also doesn't really matter for this part. The important thing to somehow get models of HoTT from such a cubical setup is you need two key ingredients. You need a tiny interval, and you need some notion of cofibration. Both of those you should have in any good notion of cubical set. And then you can look at the functor you get by restriction along the projection from this Groton deconstruction down to the cubes. So essentially you define the interval and cofibration classifier as is written there. This gives you a valid setup for the cubical model construction, and you get a model of HoTT with, for example, high inductive types. But this model, it's slightly wrong, and this will come back to bite us in a moment. But it gives you a valid model of HoTT on this category. So this is good. Now we can try to sort of fix the situation I sketched earlier. So first, we can try to define some of the key objects we're interested in, for example, for the synthetic algebraic geometry setup. So for example, oh yeah, and one thing I did not say before, this category, this internal category, if we look at it from the point of view of the internal language of cubical sets, it's of course just a category. So when I say internal language, I guess I mean the extensional type theory we have in there. But we can work in this language. So that's what I'm doing here. That's why the eyes disappeared. So we want to define this presheaf R, which should play the role of the generic ring, and it's now just defined as sending such a K algebra to its underlying type. Okay, there is already a subtle issue there. All types in this model we built here, they have some fibrancy condition attached, and this type will not satisfy it. It will only satisfy it level-wise, but it won't satisfy some coherence condition between them. So I won't talk about the details because they're quite technical, but that's something we have to fix. And there's an even worse problem because somehow we now pass to this internal site, but the objects of our internal site, we sort of strictified them in an ad hoc way to at least get strict composition of the morphisms, but there are still some objects that contain lots of paths. They are still weak K algebras. So as a simple example, you would like to maybe form this polynomial ring pointwise, so just adjoin a variable that you can now do using a HIT that resolves sort of the mismatch you had before. Now you just work with all these cubical notions. But the issue is that this in general won't be strict. I mean, maybe for the polynomial ring, you can find some fancy interpretation of this particular type to make this strict, but it will only get worse and worse. For example, if you talk about quotients, it's much harder to pull off. Instead, we use a more general technique. Namely, there is some prior work on presheaf models of HoTT, and that's the one I referred to before. But that one only considers external categories, but that generalizes to our setting. So one of our contributions, I guess, is that we take this work and generalizes to internal categories as well. but there's not that much to do actually. And one of the key technical tools they introduce in this paper is a particular modality that is called _E here. And that has the property that if you look at some notion of weak morphisms or weak natural transformations between presheaves, that those correspond to strict ones, so ordinary ones into this modal replacement. So they introduce some kind of general strictification tool. Essentially, what you do is you blow up the presheaf B a bit. At each stage, you include values for all possible restrictions, but you only require them to be coherent up to some notion specified by pairs. So it's a very combinatorial tool. And one of the key things we also get from this construction is this lemma, which we usually call the level-wise principle, but that's not a standard name. Essentially what this says, so what this modality does, I should first say, is that it makes things more coherent. It makes things behave more level-wise. For example, in the old presheaf model, it could be the case that you have things that are point-wise contractible, but not contractible. So this modality fixes this. And one instance of this fix is this lemma, which says if you have an E model type and you want to show it's inhabited, then it suffices to do it point-wise. So to produce an element in, I guess I should do it like this, in this category here. So in the model we have an internal presheaf, then it suffices to do it essentially in the slice over the objects. Okay, and we can go a bit further. Namely, we can also recognize that this construction can be factored into two parts. Namely, you can, because the thing above only speaks about presheaves, but we somehow had presheaves up to homotopy. But this construction can be factored essentially into this two-part construction where you first take a presheaf, then you map it to some notion of weak presheaf, which I won't define here again because it's somehow combinatorial and technical. But if you look at, for example, set truncated ones, it's what you expect. It's a presheaf where you replace equations with paths. And then you strictify it using a very similar construction. And this is almost an adjunction in the sense that everything only holds up to path. But that doesn't matter because this we can use to now actually work with the objects we want to define for the algebraic geometry setup, for example. So we define them on the weak side, then we strictify them. And if you want to work with them, you map them back to the weak side, insert some co-units, and then map them back. Okay. Right. So summary until now is, okay, somehow to fix, somehow to get the duality axiom, let's say, we have to pass to internal sites. And when we do this, we naturally run into some coherence issues, and to fix those, we have to work with this modality E. Okay, that's maybe sufficient for the synthetic algebraic geometry setup, but we also want other setups. So for example, there's this one of stone duality where one of the axioms is dependent choice. So our construction of presheaf models should also include these examples. And there we can sort of piggyback off another result. Namely, 2 years ago, Christian constructed a particularly nice cubical model of HoTT. The two-line sketch is, as your cubes, you choose finite non-empty posets, and then you get a particular monad on that by restriction right-Kahn extension along the inclusion from, you obtain from the inclusion of semi-simplicial sets to cubical sets. And you can show that this particular monad plays well with the notion of vibrancy, and the submodel of modal types is then really well behaved. So it's a good model of higher setoids in a constructive setting. So in particular, it's Quillen equivalent to simplicial sets. So this maybe tells you that this is a good model of infinity groupoids. Yeah, and constructively, you can observe this because it satisfies this other principle, which we usually call the pointwise principle, an analogy to the one before, which essentially says, if you want to prove a proposition, so if you want to show that the type is inhabited in presheaves over cubical sets, then it suffices to give points of it, which is also something you would expect. Okay, and this principle is strong enough to imply the dependent choice axiom we want. So this is a principle we would like our presheaves to inherit. So we have a good notion of cubical sets to start from. We somehow know how to build presheaf models over internal categories. Now we would like those presheaves to also somewhat inherit this principle from the cubical sets. Okay, and these are then, I guess, the main technical contributions. So first, you can lift this modality that Christian used to presheaves, essentially by post-composition. And then you have to show that it still plays well the notion of vibrancy you have in these presheaves. That's a sort of technical proof. I won't go into the details, but that's sort of the first ingredient you need. And then the second thing we need is that we can use both of these modalities, because before I said we somehow want to talk about, or we somehow need the strictification modality, the E underscore. And on the other hand, we also need to know this lifted modality that makes things behave more pointwise. And to do that, you have to show that essentially one preserves modal types for the others. Then by a standard result about modalities, you can combine them. Okay. And this is sort of the second main technical lemma you have to show. Again, this is a bit technical. The two-line sketch of this is that this E underscore, it's defined as a certain limit of another monad, namely the one that comes from restriction right Kahn extension of the inclusion of the object. So the one we saw 2 talks ago. And that one essentially has the property that preserves every one of these Lex operations that are lifted by post-composition. And this property is just preserved in for this particular diagram you use to build this modality. Okay, so now we are almost done. So what we would like to do is we would like to conclude that if we have a type A and it's inhabited in the internal presheaves, that it's inhabited in this slice of cubical sets, and then that hence it suffices to show that it's inhabited pointwise, except we cannot do this because of a very subtle issue, namely that a type that is fibrant in the sense of the model on the left, it will not be fibrant in the sense of the model in the middle. So not in the sense of cubical sets, but some slightly different notion of vibrancy. That's a subtle issue. And the way to fix this is to only consider certain categories, essentially. So we say a category C is fibrant if this projection from the morphism to the objects times the objects is a fibration. So equivalently stated, if the family of morphisms is a fibrant family, so this will be the case for every category you define in HoTT, and for example, strictify the way I sketched earlier. And so what does this roughly give you? Well, this being a fibration means if I have a path in the objects, then I can lift it to a line of morphisms somehow. And this joint projection being a fibration means I can also do it in a non-empty context. So this is how this pops up in the actual construction. And if I can build from a line of morphisms, from a line of objects, a line of morphisms, and I'm considering presheaves, I can use the restriction action on this line of morphisms to essentially get a transport operation. So that's the sketch of why vibrancy in the sense of this presheaf category here implies the vibrancy in this slice of cubical sets. Right, and if you have this, then you can fill in the missing step on the slide before, and that yields, I guess, this then main result. So we have shown if you have a fibrant cubical category, then this combined operation is a Lex modality. So types in the presheaf model will be modeled for both. So we have the strictification. It will be a model of HoTT because that's what the initial construction gives us, and the localization with these Lex modalities preserves this preserves these properties. And lastly, this neat property that propositions can be proven on points is preserved, which, for example, implies certain axioms you want, and more generally, dependent choice is also something you have in every presheaf model, so you would expect it in something that's supposed to be a higher analog of a presheaf model. And this gives us a general tool which we can apply to our concrete examples. So that brings me to the conclusion. So what's currently missing are some minor details in the specific applications. So we have these general strictification tools, but there are some minor gaps in checking some particular axioms. But what is done is the general theorem about the construction of the presheaves. And what would be interesting in the future, I guess, would be to compare these notions of cubical presheaves with some other, maybe classical models of higher presheaves to see whether we actually constructed the correct thing. And also, especially the axiom verification is quite brittle and sort of subtle. And I think that would be a prime target for formalization. Most of that can be carried out in the internal language of the cube category. So this would be, I think, a good candidate. Yeah. Okay. I think I'm out of time. Okay.
I think you mentioned this constructive kind model structure on simplicial sets, right?
Yes.
At some point.
Yeah.
Which one do you mean? Because I guess there's one by Gambino and also Zappler and some other people, and then one
I'm pretty sure it's Christian's because so this is some work he did some time ago. So the cubicle sets we start from. Where's the slide?
there it is.
I should just look here. Yes. Yeah. And yeah, I'm pretty sure the equivalence is with the model structure he constructed in this paper with 2 others.
Yeah. With Gambino and the
yes.
Similo.
It's called the constructive Kahnquiller model structure 2 new proofs, I think. Evan will correct me. The one by Simon Henry. Yeah. Okay. I was a bit surprised because I thought they are the same.
Okay. Thanks.
Other questions?
For the case of the condensed type theory, you're dealing with countable presentations of Boolean algebras,
yes,
axioms. That do you have any constructivity issues in dealing with that? Like, is countable choice needed when proving duality in the method?
Yeah, of course. I don't think so. So we mostly looked at the SAG application for now and this general result. So this is part of the work in progress. I'm not sure. I don't think it will be needed, but don't quote me on it. Ask me in a month, then I can presumably tell you.
That would bring us to one of my questions. So this is all about presheafs, right?
Yeah.
So, but the condensed that are sheaf category.
Yeah, it's what it's what I sketched in the beginning. The sheaves are not that great of an issue with these model constructions for type theory, because everything factors essentially neatly into 2 parts. So the role of sheafification is taken by forcing with a Lex modality. So most of the constructions, you first construct a presheaf model, prove some preliminary axioms, you prove certain types exist, you use those to then construct a certain Lex modality, and then you take model types for this one, and those should correspond to sheaves. I mean, there's a certain mismatch with the usual definition, but usually it factors neatly into these 2 parts.
I see. And for one other question, maybe. Otherwise,
I mean, one thing I maybe did not say is that this mismatch is in vibrancy is actually a key technical issue we worked on, and essentially I hinted at it, but there is a correct notion of vibrancy on these internal presheafs on internal categories, and this is not the one constructed by the off-the-shelf construction. So you don't get a model of type theory in general, but they just so happen to coincide in the case of a vibrant category. And actually, we tried to construct this model in general, and it seems like the conditions that are needed to get it are essentially equivalent to this vibrancy condition on the category. So I'm happy to talk about this if someone is interested, but it's a bit subtle.
Okay, let's do it in the break. Let's thank you again.